So we're officially opening the webinar for today. So welcome for this third episode of the React Cluster webinar series. The topic of today will be from data to decisions, how can AI and big data support decision-making in resource recovery from waste? I will be moderating today's session. I'm communications coordinator within ISWA and the iBot for CRMS project. During the webinar of today, we'll have 4 experts with us from various EU-funded projects. So we'll hear about Michalis Maniadakis from Reclaim, Patrick Canisto from ALCHIMIA, Antonio M. Ortiz from iBot for CRMS, and Cesar Arenas Prado from DARROW. They will go over the different applications from solid waste to scrap steel to waste from electrical appliances and electric vehicles and wastewater, and explore how can data-driven tools and AI technology are reshaping the future of industrial decision-making and are being leveraged to boost efficiency and sustainability and waste and resource recovery. So we will be together for about an hour and a half until 12:30. This is the webinar introduction that you see on the slide. We will then go over the 4 different presentations by the experts of today. So they will have each about 7 minutes presentations. And then the second part of the webinar would be an interactive panel discussion on critical questions around the topic of today. We will have time, about 10 minutes at the end of the webinar for Q&A from you. And then we'll conclude for about 5 minutes. Before I introduce the speaker of today, the first one, I would like to run through a few technicalities. So as you can see, the meeting of today is being recorded. So it will be made available on the different projects channels afterwards. So I invite you to follow these different channels to be made aware when the recording is available. I will share with you in the chat the details a bit later on. And then today we will be using Slido to essentially just gather in 2 different moments your input. So the first question is, we're going to go through it now. So if you would like to scan the QR code on the screen or go over to slido.com, I will switch screens and then go over to the Slido presentation for the first question of today. Which is, we would like to know which type of organization do you represent, if it's either research and academia or process industry companies, technology providers, recycling companies, manufacturing companies, industrial associations, European partnerships, more like policymakers and regulatory bodies, or civil society and media. So it looks like from now, research and academia is the majority. So I will leave this open for maybe a couple minutes so that you can see. I hope you had time to also log in. You also have the QR code on the side if ever, you didn't. But so far, okay. So we also have policy present here today. So this is essentially to have an idea on, who is present in the room today. Okay, technology providers, industrial associations. So it's very varied, actually. Recycling companies, very nice. Okay. So I will leave the Slido open for a few more seconds, so then we can also have this information later on. I invite you to continue voting, and then I will go back to the presentation quickly to jump over. So here we go, up. So the first part of this webinar would be essentially to go over different presentations by experts. So the first expert of today is Michalis Maniadakis. He's a researcher, and he's working at the Computational Vision and Robotics Laboratory at Force ICS. He's specialized in machine learning and cognitive robotic system, and he's been pursuing research for about 20 years. And he's currently the coordinator of the Reclaim project. So without further ado, Michalis, I'll give you the floor, and you have about 7 minutes for your presentation.
Are I supposed to hear something now?
Yeah, can you maybe unmute? I cannot click on my side, but you should have the button, Michalis.
Okay, yes,
yeah,
yes.
perfect, perfect. Yeah.
Can you see my screen? Okay,
Yes.
okay. So sorry for this confusion. Sorry. So yeah, I'll discuss about the Reclaim project and how we treat big data for our AI purposes. The full title of the Reclaim project is an AI-powered portable robotic material recovery in a box. This is a project that is implemented by 10 partners coming from 5 different countries. And regarding the problem that we're going to address in Reclaim, this is focused on the waste that we all as citizens produce. And what happens with this waste is that they are collected and they are transported into central places, material recovery facilities. These are the MRFs close to the urban areas. And there they are processed in order to recover valuable materials. This happens either manually or automatically, but this is not a big issue here because the centralized model that we follow up to now is not efficient for remote areas and for sites where high volume of waste is produced in a very short time. The reason why this is not efficient is because it is very costly to transport the waste to the central MRFs. The waste is usually compressed inside trucks. So this makes the recovery of the sorting of materials more difficult. And at the end, we have less materials recovered. So there is a need for a portable material recovery facility, and this is exactly what we are doing in Reclaim. We are developing a low-cost and portable and robotic material recovery facility that is able to sort waste at a local scale, but with an industrial level efficiency. And this is more cost-effective, mainly because we save a lot from the transportation to the central MRFs. This video shows what happens inside this MRF, the container that is full of technology, robots and cameras and AI. You see that there are 5 different robots installed inside the PRMRF that they can pick and sort waste into different bins depending on their material type. To make this real and more efficient, actually, we have developed our own robots, which are some very low-cost robots that are doing the picking and the sorting of the waste. These are linear robots with either 1.5 degrees of freedom or 2.5 degrees of freedom. The 0.5 degree of freedom refers to a piston that moves up and down with a binary mode, and you see that things can run quite efficiently. Now, regarding the decision making, we collect a lot of images from waste images that are processed and are used to train our models in order to be able to categorize, identify and categorize the waste objects. An example is shown in this figure. We want to categorize objects as PETs, aluminum cans, or HDP bottles. You understand that the waste images are actually endless. There are different deformations that they may have is endless. So what we do instead of recording millions of images, we are also trying to produce our own synthetic data. And this is what is shown here. We start from an original image on the left, and then we do random transformations in order to produce new ones, new appearance of this object. We have trained a model that can assess the realism of the produced images, and you see that on the right, we can develop new, quite realistic synthetic images. that are used to train our models. On top of that, there is also the option of having a dual spectrum categorization, which means that we can categorize the waste in both the visible domain and the infrared domain. This increases a lot the accuracy of our decisions. And in fact, what happens is shown in this video. You see that by combining the two, actually both categorization approaches have their pros and cons. So by combining the two, we can have at the end a very highly accurate decision-making procedure that goes up to 98.5% of accuracy. Overall, the container that we have developed is a full system that can be easily transported and deployed in less than an hour. The video shows here what our participation in an exhibition where the whole container was transported and be ready to operate in less than an hour. The PRMRF that we're developing can recover up to 7 different material types. The ones that are shown in this slide: PET, PE, PP, polystyrene, 3 cartons, aluminum, and ferrous metals. Regarding this performance, it can pick on average 120 items per minute, which overall goes to more than 50,000 items recovered per shift. And this is the system that actually next week we will start processing waste in Kefalonia Island. I mean, these are real waste that are produced by the citizens and the visitors of the island. So we will be in contact with the real demands of waste sorting. The image on the right shows what happens now in the island. So the whole waste stream is collected and transported to the mainland for processing. This means that we transport both the recyclables that have a value, but also the residue. And after processing, the residue have to go back to the island for land filling. I think that you can understand that this is quite costly, but this is not the worst that we have experienced up to now. This figure shows what happens in the Pacific Islands, where they use airplanes to transfer their waste in central places for processing. So this clearly shows the need for a small-scale waste processing unit. That is the one that we are implementing in Reclaim. And with that, we believe that we propose a new model of the circular economy that is based on the decentralized waste processing, small and local scale. And what we achieve is industrial level efficiency for sorting waste, much less transportation of waste. We believe it improves the material recovery because the waste does not need to be compressed, and clearly this creates opportunity for new businesses and new jobs. That was all. Thank you for your attention, and yeah, we may go. Thank you.
Thank you, Michalis. So now we can jump over to the other presentation of this morning. So moving from municipal solid waste to the metallurgy industry. So Petri Canisto is a researcher of industrial software systems, and he currently works on data-driven software architecture for controlling steelmaking. And he's a researcher at the BFI and within the ALCHIMIA project. So if you want to take the floor.
Okay, thank you very much. Can you hear me?
Yes.
Great. So thank you for the introduction. So it's only 7 minutes, so I cannot cover in deep, but just to briefly give you some motivation and the background of the project. Now it seems that it went black for me now that I use the full screen. So, but maybe just a second. It's better now?
Now it's okay. Yeah.
Okay, great. So, but the project goals and problems that are behind where the motivation comes from. The variety of optimization models we need in this project, and then how to optimize scrap reuse, because in the end this webinar is about waste and reusing waste in a new way. For the motivation part, what's behind, so of course we are aiming at circular economy, that's an important element, but then on the other hand, these processes for circular economy are not easy to control, so we need decision support for the operators. In steel plants in this case. Steel is a strategic resource, so we want to make steel in Europe also in the future. Steel is more or less everywhere, you could say. So that's why we want it to be economically feasible so that these steel plants can truly remain in Europe. On the other hand, we want to save energy and we want the processes to be efficient. And this everything, all of these goals can be reached better with data-driven approaches, as you can see at the bottom. So data enables reaching these goals. Just briefly about the partners, not going to explain one by one, but in the middle, you see the use case partners, CELSA Group and Fonderia di Torbole, or FDT, are the two industrial operators in this project. So first about the CELSA use case, which is the main use case regarding this presentation. So the aim is to make new steel products from scrap. And you could intuitively think we just melt the scrap and then we have steel, but this is not the truth because the scrap comes in many sorts, in many qualities. Some of the scrap types are purer than the others. Then on the other hand, the steel products also vary. So they have various requirements regarding chemical composition, for instance. So there's plenty of steps, and we don't focus on all of these in this project and in this presentation either. But just to give you an overview, there's multiple problems, and all of this can be facilitated with data, transforming scrap into new products. The other use case, which receives less focus in this presentation, is the FDT, Fonderia di Torbole. So producing automotive parts from steel. It has still environmental impact reduction as a goal, and also cost reduction, of course, quality standards, and then keeping them processes efficient and not causing too much waste. As a novelty from this project is federated learning, and as a method, this is something that has been applied for some time already, but not so much in steel making. So what's behind here, as we have these optimization models, these are operated in plants, in steel plants. And if these plants are many and they have some symmetric elements or maybe even similar models, or let's say almost similar models, we can improve the performance of these models by centrally letting the models learn from the other models centrally. So we have this central server that performs federated learning by receiving local updates from the plants, and then on the other hand sharing the global model weights with the plants that operate the models. And this is beneficial, especially if the data coverage is limited. So there can be some, for instance, some exceptional situations that have not been faced in some of the plants. And when the plant faces the situation for the first time, it is beneficial if it has received already some knowledge about this from the other plants. And the other related item to talk about on this slide is the continual learning. So the idea here is to monitor the performance of the models and then retrain the model or regenerate or reparameterize the model if it seems that the performance has degraded. And this is something that's going to happen if you use scrap. Scrap as input material is fluctuating. The quality rarely stays very stable. Then the final slide about this variety of models. So we use AI, but not only AI, but other models too. So on the left, you see we have scrap characterization and scrap mix optimization. These provide decision support to the operator. So if we want to produce a certain scrap type, which scrap type, certain steel quality, which scrap type should be chosen as the input recipe. None of these two models are AI. Then on the other hand, we have this dynamic process model, which operates online as the electric arc furnace that takes the scrap, melts the scrap into steel. This is not AI either, but in this project, we are researching using federated learning to parameterize this model. So even though federative learning comes from the AI scope, it seems that it is applicable even for a dynamic model. Then finally, we have this later furnace model, which is a subsequent process of the electric arc furnace, and this is an AI model. So like you can see, if you just have proper interfaces, the models can actually use the results from the other models and also integrate methods like federative learning. Thank you very much for your attention.
Thank you very much, Petri. So we're going to move now from metallurgy industry to waste from electrical appliances and electric vehicles. So we have Antonio M. Ortiz, who is currently a senior researcher within NOSE, where he focuses on the development and the coordination of EU-funded projects. He has international experience in ICT, security, and innovation research. And he's the technical coordinator of the iBot for CRMS project. So Antonio, the floor is yours.
Thank you. Thanks, Leah. My part of my presentation is focused on how to recover critical raw materials from urban waste. So to start with, I would like to explain why critical raw materials are important. Well, critical raw materials are strategic materials which are necessary for manufacturing key technologies. We all have a phone that needs lithium, cobalt, etc. Some of these critical raw materials that are needed for it to operate properly. The main issue with this kind of materials, why they are critical, is because the production is concentrated on a reduced set of countries that are in some cases limiting the export of these materials. So their availability is reducing. As you can see here, for example, China controls most of the production of magnesium, graphite, or other rare earth elements, etc. So it's key for Europe to recover as much of these critical raw materials as possible from waste in order to be reused in further manufacturing processes. In fact, the European Commission has set a high priority for this in order to keep sovereignty and resilience in the world industry. So they have published the Critical Raw Materials Act that details all these needs about keeping the raw materials that we have and recover it from urban waste mainly, that so we can become more and more independent from the producers of these critical raw materials. So currently, the situation for urban mining, so recovered materials from urban waste, is mostly manual. So there is manual sorting from residual waste, also manual sorting from shredded products, manual disassembly of products in order to recover these materials. Here, for example, it's shown the recovery of magnets from hard disk drives. There is also manual dismantling of different components or different electronics or other appliances, and also the recovery of materials from landfill is not fully explored. The thing is that currently, with the volumes of waste that we are generating nowadays, the manual processes are not sustainable anymore, and there's no possibility to solve the current crisis. So in order to solve this, what iBot for CRMs is working on is to enable AI-powered self-learning robots in order to first valorize or estimate the value of the waste, and then perform this recovery of critical raw materials. The project started by the end of last year, so we are still in the early stages of the development. So regarding data and AI in the project, what we do is we have multimodal sensors. We have RGB cameras, LiDARs, XRF, etc., in order to collect all the possible information. Then the idea is to integrate this information, this data with AI or machine learning models, so to enable big data analytics. There are real-time feedback loops in order to increase the accuracy of the models, as well as integration with digital twins, closing the circle again for getting more additional data from sensors. Then regarding the decision-making process, so first we perform data collection and processing in order to identify the different materials that are available in the waste streams. There is also an assessment about the potential value of the materials that can be recovered and the risk of recovering them, the risk of the cost. We need to make this estimation of the trade-off between the effort that recovering this material represents and the value that they can provide. The system will make autonomous sorting decisions, so autonomous picking path planning for the robot in order to take the appropriate materials from the waste stream. The system will learn from experience through reinforcement learning approaches, and there will be traceability and explainability throughout the whole process in order to, with the passage of time, optimize the process as much as possible. So this is the end of my presentation. Thank you very much.
Thank you, Antonio. So for the last presentation of this morning, we'll move from urban waste to wastewater. So Cesar Arenas Prado is an engineer focused on process improvement and data analysis. His experience is in healthcare, automotive, mining, and the construction sectors, and he's currently a pre-doctoral researcher at the CIT Centro Tecnológico and a member of the DARROW project. So Cesar, you have the floor.
Okay, thank you so much. I'm going to share my screen. Okay. You see me, right?
Yes.
Okay. Well, thank you so much. Yeah, thanks for the introduction. It's for me a pleasure to be here. Yeah. As you said, yeah, I'm doing the PhD and I work with the SAID and the DARROW project. So the issue of the webinar is that from data decisions, how can can big data support decision making in a resource for a recovery from waste? Okay, so this is the agenda where I'm going to skip some parts because I'm going to tell you more about the project. Well, the wastewater plants are really complex facilities because it involves multiple knowledge for being managed. We need some physical knowledge, chemical knowledge, biochemical, biological, because in these facilities, we receive all the water from the outside, from cities, from factories, from agriculture. It contains a lot of pollutants, many kinds. So, well, we establish inside the facility all a treatment, all a kind of treatment to reduce the quantity of the pollutants, in order that when this water goes out to the river, go in a good condition and doesn't cause any bad effect on the environment. Okay, so that's what a wastewater treatment plant does. Now, our technique is focused also is focused on integrating the knowledge from mechanistic models. The mechanistic models are like mathematical models that have been studied for several years. Physical, you have like many equations, you have matrix and steady state equations. So all this knowledge we want to approach and combine it with IM models. So it's going to be like a strong model. If we know the mechanical and the interpatterns of a wastewater treatment plant, we can deduce an AM model that will predict how is going to be the behavior of the plant. So that is our main hypothesis. Now I present the DARROW project, that is a European project that wants to become from waste to, that wants to increase the technology in the wastewater treatment plants. But why they want it? Because they want to reduce the energy consumption, because the plants consume a lot of energy in the aeration process. We reduce the greenhouse gases. Of course, the plants produce greenhouse gases, for example, the nitrogen. Reduce the waste in the process, chemical consumption, and increase the water quality. Well, is the motivation with the DARROW and how it's going. We are working together. Okay, so I explained basically the water comes from this part. This is the physical process, settler process, and in that area is the biological process where all the magic happen. No, we have the aeration process and the biological process, and after that you go to some settler secondaries and goes out to the river. But here you have some facilities, extra facilities. This is for the sludge. This water, when comes with the sludge, and this sludge it's very rich in components, in organic components that and those components are suitable for example, for agriculture. And also these components can produce biogas, and the biogas produce energy to the same plant. So it's like a closed circle that provides itself. So it's that with the objective of the project, to improve all this process. Okay, so and our technical approach or our technical strategy is to use the mechanistic models that come from the past and create a lot of simulations, like 1,000 years of simulations. That's a lot of data. And we use machine learning models to catch the patterns, to catch the trends, to catch all this internal information that is hidden. And for what? And why? Because we want to create a decision tool. This decision tool is going to be like a support for the workers, for the collaborators inside the plant. Because as I told you at the beginning, you need a lot of knowledge for physics, chemistry, or biological. But with a machine learning model, we can predict the behavior of the plant, and we can give, after an optimization process, a suitable recommendation. So the adaptation for the workers or the person that is involved is going to be faster. Okay, so this is the gap that we are going to try to get, to fill. Sorry, this is the gap that we are trying to fill. This is a space that is between the technical knowledge and the practical knowledge. Okay, this is the sketch that we use. This is the BSM2. If there are somebody from the industry here knows that it's in a standard in this sector. And the data frequency that we are using is hourly. The software is the WES, and we have 6 kind of scenarios, like very rainy and very dry. Okay, so we generate like 1,000 years of data, and we establish our database. So we have information in the past, in the present, and the future. The influent comes with a lot of pollutants, okay? Nitrogen, ammonium, phosphorus, many things. But you have operational data. like the controls in the aeration system. Okay, combining it with the biomasses, you will dissolve the pollutants, and you will see it on the effluent. Okay, and also consuming energy. So if we have the data, the data in the past, in the present, we could be able to predict in the future. That's why we use those AM models. For this information, we choose like LSTM because they gave us some good results, because it's like a temporal series. No, maybe we can go deeper on a technical process if somebody want to ask me about that, but I'm going to go faster by this way. After we have a suitable model that can predict, also I didn't say, but we are able to predict like between 12 and 24 hours with a good accuracy. Okay, so after that, we realized that if we change the set points and we predict, we're going to get the results. And if these results commit with the European restrictions for the effluents, for example, it's going to be a good solution, but it's going to be optimal, not necessary. And we change again the set points and predict and see if it's optimal. When we have a battery of simulations, we can determine if it is optimal or not. For that, we use something. Our tests are being with genetic algorithms, just for generate multiple solutions. This is the strategy. No, at the end, it's a multiple objective minimization problem. So that's how we do the optimization process. I take it as a references from another investigation from Korea. So no, this is I just took from them and try to adapt to this investigation. That's something that we are going to see at the end of the process. No, now we have the effluent, we have the influent, we have our set points, and for the next, for example, next 8 hours, we are going to establish our set points in this, in these points for being efficient for being efficient, and it's going to be our cost and our effluent quality. So that's what we are trying to do, that we are working now, and just for make the people make the job of the people easier. That's how the AI can help the people to take informed decisions by the end of the day. Okay, well, I think that's all by my part. If you have any doubt, please just let me know.
Thank you very much. Can I ask you to stop sharing? Yeah, that's perfect. Thank you very much, Cesar. So we're going to move now to the interactive panel discussion of today. So just it was very interesting to hear about the use of AI for these different waste streams and sectors. So just for reminder, before we jump over, we had Reclaim on municipal solid waste, ALCHIMIA on industrial waste, iBot for CRMS on urban waste, and DARROW on wastewater. So they all have this joint goal, though, which is resource recovery and the usage of AI to collect data and to improve efficiency. So associated to that topic, I have maybe a first question for Michalis and Antonio. I would like to, you both mentioned, the use of robots in both Reclaim and iBot for CRMS. Could you explain how this data is used for robot control, and how can you evaluate if the robot made the right decision? So starting with Michalis.
Yeah, thank you. As we mentioned it was mentioned in my presentation, this data, the collection of the data, the images of the waste are used for training the models that then provide the goals for the robots, what needs to be picked and where it needs to be placed. Now, regarding the evaluation of these decisions, this is a really challenging task, actually, because as I said in my presentation, 100, on average, 120 decisions are made every minute inside the PRMRF, inside our waste sorting container. So it's hard to evaluate each one of these decisions. On the other side, this high number of decisions can actually help us to understand if there is a constant pattern, a mistake pattern that is done from our decision-making mechanism. And this can be accomplished relatively easily by doing some kind of statistics. So that was actually the case in one of the problems that we have faced when debugging our system. In fact, after looking the bin where aluminum cans were collected, we realized that there were in the same bin some small size Tetra Pak items. These are paper items, which were located there by mistake. We searched somehow what was the reason behind that, and we understood that we have introduced a bias in our model to consider as Tetra Paks only the big size items. So the smaller ones were shifted to the Tetra Pak bin. We understood this problem that we have introduced into the model. We switched that bias, and everything worked much better. So by doing some statistics, we can evaluate the decision of the models. But in the Reclaim project, there is also another option for evaluating the decisions of the robot. And this is based on a game that we have developed. So we let the citizens re-evaluate the images that our robots have evaluated. So if, let's say, 9 out of the 10 people disagree with the decisions of the robots, then probably something is going wrong, and we have to reconsider these erroneous cases. What we typically do is that we take these images with where the robot has made many mistakes. We as experts annotate the images, we provide the correct results, and we use them in the training data in order to improve the decision mechanism of the robots. And this was a pattern, a procedure that has increased the performance a lot. Yeah, that's all from my side. Thank you.
Thank you very much, Michalis. Antonio, could I have maybe the perspective of iBot for CRMs?
Yes, thanks, Leah, and thanks, Michalis, for your answer. In fact, we are now at month 6 in the project, so our solutions are not yet very advanced, but we have planned activities first for collecting data using, because for the waste streams, in order to identify and recover the critical raw materials, sometimes there can be occlusion problems. The materials that we wanted are hidden by other waste components, etc. So in that sense, we will use hyperspectral cameras and XRF, so X-ray fluorescence, in order to accurately locate and identify the materials that we want to recover, to extract from the waste stream. So in that way we understand the waste flows, what's the variability, the heterogeneity, etc. So what are the characteristics of this flow, and what is the best way to recover the critical raw materials. How we evaluate the accuracy of the robots. This is or the performance of the robot operations. This is something that it needs to be. What we have a plan is to compare it to the human decision. So evaluate, putting together a human and a robot, and see the differences between both decisions in order in the first stage to train the AI algorithms that drives the robot, and then to reinforce their their behavior in order to optimize the collection of critical raw materials. Also, there's in the end we will compare the amount of critical raw materials recovered both from the robots and by the human operators in order to evaluate the accuracy and the performance of the robots themselves in comparison with the human operators. Here there is something, some aspect that we need to be we need to pay a lot of attention, which is safety, in order to, because the idea of the approach of the project is to have collaborative robots in the same line together with the humans. So how to establish this human robot teaming or human robot collaboration is something that we are working on also in the project.
Thank you very much, Antonio.
Yeah.
I now have a question for Petri. So we're moving from robots to a different usage of AI in decision making in complex recycling scenarios. I would like to ask you if you can elaborate on how AI methods and non-AI methods can cooperate for data-driven decision making as shown in ALCHIMIA.
Oh, thank you. So methods and non-AI methods is already something that I briefly explained in the presentation. So, but like I'm also showing in the presentation, a steel plant is complex. So there are multiple processes included, and they have different dynamics. So for some of the processes, it can be beneficial to use an AI method, whereas for some of the processes not, or let's say some of the aspects. So think about the electric arc furnace, which takes scrap as the input, steel scrap. We have been using statistical methods to characterize the scrap types, so to know the chemical composition of the scrap, for instance. So if we put these scrap types into the furnace, what is the output, what is the chemical composition we can receive? This enables us to, let's say, go backwards in the process and infer what chemical composition of the input materials was. And then on the other hand, having this variety of the models, so regardless of these are AI or not, we just specify interfaces between the models. Or if it's about federated learning is, let's say, by definition, we have this centralized external actor that creates a global model from the local models of the multiple. Well, if we talk about steel making, the models of the plants. So this is also considered an AI method, but like we see, not necessarily, it seems that we can also use the parameter as a dynamic model, which is a dynamic model that we are using for the electric arc furnace that melts the scrap. So let's say we only have our imagination as the limit here, then of course also the properties of the processes. So maybe not everything, not all methods suit for all processes. So this enables us to choose what we need and what suits best for the needs.
Thank you very much. I have one last specific question and maybe more of a common one after this. This one is for Cesar. We would be curious to know about Darrow's data collection approaches and how AI is used to optimize the performances of processes. I cannot hear you,
are muted.
Yet. Yeah.
Okay, thank you for the question. I'm going to share my screen again to explain it better. Okay, the data collection is very important for us because we create a battery of simulations, like a lot amount of information from the past, present, and a future. This information is based on physical rules, on physical rules. So it's it's very similar to the real issues. So we cast that approach and we set up our models. So because we have a lot of simulations, we have a lot of scenarios, we have a lot of combinations that give you a lot of information to learn how is the behavior of our plant. So it's a very important point, and that is the strength of this method, because we combine the theoretical experience and the practical experience, and then we can take some decisions based on the optimization process. Based to the now going to the second part of the question, the optimization process is an iterable process that change the set points, change the operational points in the plant, and predicting it with these set points. With the influent set points and predictions, we will be able to see if the prediction can meet the constraints and if it is optimal. So what are the rules for the optimization? Well, we have the effluent quality index, that is a combination of the main pollutants that we have to avoid in the effluent. So this effluent has a weight. We establish an equation, establish some boundaries also that are the limitation from the European Union. We have the operational cost index, that is the cost of the operating the plant, and we have the methane production, that is going through another line, through the sludge line. Combining these factors, we have a multi-optimization problem, no, that creates many possible solutions. With a genetic algorithm, we choose just a good one. Maybe it's not the best, but it's a good in a reasonable time. So that is how our optimization process works. Yeah.
Yeah, thank you. That's perfect. So I have one last question for the panel discussion, which is essentially going to be addressed to all four of our experts. So the projects are all developing solutions that we hope will be uptaken by the industry. So what are the challenges that you foresee arising from that? And do the solutions that you mentioned scale up also? So maybe we can keep the same order. I can start with Michalis.
Yeah, thank you. Actually, as I noticed in my presentation, the system that we have developed is already installed and is ready to operate by the end of this month in Kefalonia Island. It will process the waste coming from the citizens. And it is certainly a scalable solution that can be copied and applied in other islands as well. In Greece, we have many islands, but in Mediterranean too. But I mean, there are many places around the world that this small unit can be of use. The main challenges for that regards the quality of the input waste stream. Usually in the large industries that process our waste, there are several steps that waste are filtered. And we assuming for the operation of our system that there is a certain quality. What we assume is the PMD, the plastic metal drinks quality. This is a known quality type for waste across Europe. So if we have this as an input, we believe that our system will perform really well. So the main challenge is to guarantee this quality for our input. Thank you.
Thank you. Antonio, maybe could I have your input?
Yes, sure. Thank you. Well, regarding the main challenges for iBot for CRMs, from the technical perspective, we need to make everything work. So from integrating the vision systems with the AI and with the robots in order to efficiently recover the critical raw materials, this is the first challenge. The second challenge is about adoption and exploitation of the project results, because in order for the solutions provided in the project to be widely adopted, it is essential that it's profitable for the waste management plants. But if the situation continues with the producers of critical raw materials limiting the exports to Europe and to other countries, the prices for these critical raw materials will continue to increase, and there will be a situation in which we need to recover them no matter how. So, but the idea is to make it the process is efficient and profitable for the waste management plants in order to maximize the recovery of this kind of materials.
Yeah. Thank you.
Thanks.
Maybe on the ALCHIMIA perspective, Patrick, can I hear from you?
Oh, thank you. So first about the challenges of the solutions being adopted in the industry. So when there's some software-based system, in the end, okay, you have software and then you have hardware. And in our case, the hardware is in the end the process equipment. So that's operated by the plant operator. And this software, this optimization software, comes from us. As long as we are in the research project, we are developing everything, the researchers are there, the researchers are available, they are trying to reach the goals of the project. But once the project is over, then it means that either there must be some sort of, let's say, service model for somebody to maintain the software, the models, or the operators must adopt the knowledge by themselves. Because basically no software is today something that runs infinitely. You will have to update it. Maybe the plant operator installs a new sensor or new camera or something that adds, let's say, new ways for the software to optimize the process, or maybe there's some security related that must be updated. So this is truly something that must be negotiated with the operator during the project or after it soon. And then about the scalability, the models run inside the plant, so this doesn't really cause so much scalability problems. So even if the model runs in real time, if you just have the sufficient resources, no issues about that. But if there's a network of multiple plants and you use federated learning, this means that there's a centralized server that's going to collect data, or collect weights from the models and then share the global model back to the plants. But this is something that happens offline. So I don't expect anything very serious about this. So if it happens offline in the background, it doesn't really affect the operation of the real-time processes. And federated learning, as far as I know, it has been applied in scenarios with plenty of clients before. So even though I haven't developed algorithms by myself, I believe this should be no issue in federated learning.
Thank you. And yeah, Cesar, maybe.
Yeah. Well, I was thinking the wastewater treatment plants world, and well, in any plant, each plant is so different between themselves. Okay, so are like, because every city has a different situation, and any kind of the pollutants are so different sometimes. But for the scale process, I am optimistic, because one time that we understand all the complete process, we are going to be able to replicate in another plants, yeah. But considering their own difference between them, no. But the workflow is going to be almost the same. So I think that the AI is going to solve many issues about energy efficiency, no, helping to the operators to take good decisions. That's another challenge that Petri was talking about, the operators, because we have to gain the operators' trust. Okay, we need that they trust in our models, they trust in the technology, because the AI now it's like it's going to remove some jobs, it's going to to fire people, but it's not like that. It's not like that. No, it's just coming just for helping people to make their job easier. Well, also I think they integrate it with a real plan is going to be also a good challenge, because the sensors and the information sometimes are not really reliable. That's it's something that we are working on just on this moment with partners, but it's going to be a challenge that it would be very exciting to succeed. So that's my opinion.
Thank you very much. Yeah, so I think for the panel discussion, we are coming to the end of it, but right now we have time, about 10 minutes for Q&A. So if I take over the Q&A box, I think we have a few questions already from the audience. The first one, which I believe should be addressed to Michalis, is which methods are used to generate synthetic images for training, and how do you evaluate their realisticness? Quote unquote.
Yes, this is a very practical question to the point. What we do is that we use elastic deformations, actually. So we apply a grid on the image, and we try to make many small movements on this grid. And we can do it for, I don't know, for some thousands of times. So we can come up with some very strange appearances of the objects, but also some very realistic ones. So this is what is done for the generation of the images, and then for the assessment of the images, we have just trained a neural network to assess how realistic they are. So this is pretty much what the GAN approach is doing. I'm pretty sure that the person that made this question is aware about the GAN models. So we have copied thus the discriminator. We have developed our own discriminator similar to what is done with GANs. Thank you.
Thank you. Yeah, I have another question from the chat, maybe to Antonio. What are some of the methods you use to ensure traceability and explainability?
Yes, thank you. Well, for traceability, the idea is to use different mechanisms. Of course, version control for the different code developed in the project, the models, etc. Use metadata standards as well. So the idea is that we can, if we find an error or something that we want to redo somehow, we can revert in order to see why the AI maybe has made this decision. Regarding the explainability part, the idea is to use white box models whenever feasible, so decision trees, linear models, etc., in order to make it more easy to explain the decision that the AI has made in the project. Of course, having a human in the loop annotations, so we can teach the models to learn or to think similarly to humans, and also, of course, the traditional documentation, interactive dashboards, etc. Always with ethical and legal explanation reports in order to guarantee that any AI decision is compliant with applicable regulations and with the ethical recommendations.
Yeah, thank you very much.
Okay.
So there is another question in the chat. So to Petri, thank you for your presentation. I have a question regarding the use of federated learning and continual learning in production environment. Does the reaction time or latency impact production efficiency? And are there any studies in this project addressing this aspect?
Okay, thank you very much. An important question. So federated learning is not used online, but it's more like a background piece of functionality. So like we know in process control, you sometimes have response times, or you want to know, for instance, what is the temperature of the process in real time, or you want to see the events, temperature measurements, and so on. And this is not something where the federated learning is involved, but it's more like background activity to improve the model in the long term. So in this sense, it doesn't really, let's say, it is not critical regarding the response time. And the continual learning part, I would say it is more or less the same, because if the goal of continual learning is to notice when the performance of the model has degraded, and it should be regenerated or retrained. And this is not something that is noticed immediately. So the dynamics of the processes are slow. And so if I say that, for instance, electric arc furnace, the process takes like about 60 minutes to finish. There might be differences, but let's say this is the degree, so 60 minutes more or less. And actually, you are most likely going to observe multiple processes before determining that now it seems the model doesn't perform very well. So we don't have that strict or fast response time requirements regarding continual learning either. I hope this clarified it a bit.
Yeah, and in case anyone has any questions, you also have every LinkedIn pages and websites and emails in the chat, so you can always reach out also and continue the conversation offline after this. I have a question for Cesar about how do you think this AI-based approach compares to traditional operational classic expert system in wastewater treatment plant?
Well, there is something that we were talking inside my group, but it's going to be a decision tool. A decision tool is suitable for adopt an informed decision. So that's the big difference, because the old systems are rule-based and they are very strict with that. When they observe some variation, something that is not preset, pre-established, maybe it can cause some kind of conflict. So when we apply the AI models, we just work with the information of the real plant, and we can establish the rules that these plants works today. Also, there are many things that we apply. For example, for detecting if something is going wrong, we can detect, we can establish some models with the same information. And we can, well, we predict the effluent. It gives you more information to the operators. So it's like more efficient and it's clearly. So we think that's the big point for that tool, to implying that tool on this process. And also the environmental caring, because getting efficient in this process is really important, because we affect directly to the nature, and we do that, and we cannot allow to do it bad, because we are contaminating. This is going to be really bad for the world that we are trying to care. So, I want to tell something, because those few weeks a lot of people was saying that the AI is like consuming water and is going to finish with our water. Something like was trend topic, you know, because many people was publishing like photos, like images created by AI, but it's not really like that. The technical industry, the technical industry, concretely on the servers, on the infrastructure, yeah, of course needs water, but the water that the AI needs for the refrigeration process is just the 0.2% of the global consume. There are a lot of industries that consume a lot more. For example, agriculture takes the 70% of the total water. The industry takes the 20%, and the houses take just the 10%. So it's a short percentage that we use for the AI. So don't be desperate for that.
Thank you very much.
You're welcome.
Thank you, Cesar. So I think like we are running out of time for the Q&A section. So once again, if you want to continue conversation offline, I invite you to check out the links in the chat box. So I will share my screen again for essentially one last interactive sort of question for you. So if you want to head over to the Slido, we would like to hear about essentially, what are the main takeaways that you have from the panel discussion that we had, and what did you get from it? Or like, this is a word cloud, so this is an open open question essentially, to hear from the last hour, what did you learn, or what do you get from that conversation? So I hope, I see people participating, so you still have the QR code on the left side, and you can always, enter slido.com also with the number. So I will give you a few seconds to maybe connect and give your input on this. It's also very welcome. Okay, so very interesting. AI is helpful in managing data. Yes, it is. Definitely. Very interesting projects, very promising. Okay. So for now it's stopping. I will leave it. Okay, perfect. So thank you very much for your input. Just that was one last interaction with the Slido. I would just quickly, before closing today, I would like just to ask our experts essentially about if they identified any areas of collaboration today, and if maybe Michalis, you can start, and if you can tell us if you identify those today.
Yes, it's a bit tricky to find an area of collaboration with the waste treatment, but certainly with iBot for CRMs, I think that we share some common approaches that we can discuss further, and I mean change our points of view and some good practices for dealing with the flows of waste. So yeah, mostly with the iBot for CRMs, I think there is space for collaboration.
Yeah, thank you. Maybe Antonio to follow on that.
Yes, I tend to be a very collaborative person, so I try to find collaborations anywhere. So with Michalis, of course, for the part of the vision systems identification of different components in the waste streams, I think that could be very interesting. And with Petri and Cesar, mainly for the AI part, that could be something that we could elaborate or discuss further on for the continual learning approaches, etc. I think that those could be potential paths for future collaboration.
Thank you. Maybe Petri, do you want to follow up on that?
Oh, thank you. So let's say we have quite a broad area of themes, although there's this common theme of reusing waste. But so think about my own employer. We are quite deep in steel making, but this is not the whole story, because we have these EU projects. We often have, let's say, quite a wide range of use cases. So if the common theme would be like, again, circular economy, for instance, that's already something that combines us, obviously, because we are in this webinar. Industry 5.0, you have these themes of sustainability, human factors, and resilience. So I would believe that we would come together quite well in some Industry 5.0 project. And I think Cesar was the one who mentioned that there might be some human resistance because this is disrupting. So circular economy is something that hasn't existed really, well, to some extent, but not to, let's say, sufficiently before. So it is going to change the society, and we will have to think about the human factors also. So let's say I can see that if there's just a project proposal, it would be possible to build a common umbrella to involve these projects. And then, of course, the methodological side also. So if there's anything related to models, that's another question.
Yeah. Cesar, would you like to react on that maybe?
Well, I'm agree with everyone. Yeah. Well, for me, it's very interesting. All you, for example, the artificial vision is like a field that I feel curiosity for that. I'm very passionate for that, and I developed something, but I would like to apply it more, but in an academic way. But I would like to apply more, for example, with Michalis and the AI and the reinforcement learning. It's something that it's going to be the next step. For example, for my optimization problems, we can apply a reinforcement learning, for example. We can connect it directly with Antonio, with everyone. We can just put it into the plan. It's going to be costly, not as money, even as work. Also, as Petri said, it's a disrupting technology, so it's going to be costly, but it's going to be good for us, I think, and for everyone, because the AI must work for the humanity, not by the opposite.
Definitely. Thank you very much. I will share my screen. So one last time for just communication purposes. So once again, you have all these links in the chat if you want to collaborate further, discuss further, and exchange and build everything together. So thank you very much for attending today and for taking the time this morning for this webinar. Thank you to our 4 experts also for their presence. And I guess have a nice rest of your day.
Thank you so much to you, Leah.
Thank you, Mark.
Thank you very much.
Thank you very much. It was a
Thanks,
pleasure
everybody.
to join present.